Welcome to the Mechanics of Solids lecture series. In this series of videos, we're looking at examples solving for shear stresses in beams. The objectives of this lesson are to be able to compute vertical shear stresses in beams of different cross-sectional shapes. And putting this together with previous knowledge that you've learned, you should be able to analyze loaded beams for both bending and shear stress. In this first example, we're given a cantilever beam with a couple of point loads, circular cross-section, and we're asked to evaluate the peak normal stress sigma x due to bending and peak shear stress tau due to shear force. So find sigma max and tau max, and both of these logical units would be KSI. The approach to this problem, we need to be able to find the maximum internal shear force and the maximum internal bending moment in the beam in order to find the stresses. If you can recognize the maximum and where they occur, you may not have to draw a shear and bending moment diagram, but we'll go ahead and do that for illustrative purposes. Starting out by labeling the end as support A, we'll calculate the reactions, a reaction A sub y in the vertical direction, and a reaction moment at the fixed support. I'm drawing them both in the direction that they will occur. The vertical reaction is going to be positive to balance out the loads and is simply equal to the sum of the forces, 20 plus 40 or 60 kips. The moment is also going to act in the counterclockwise direction to balance the loads that are acting on the end of the beam, and I can evaluate it simply as the contribution due to the point loads, 20 kips times 5 feet plus 40 kips times 10 feet, which computes to 500 kip feet, acting in the direction as shown. So I will quickly sketch my shear force and bending moment diagram by extending lines down. Make a label for the shear force diagram, V in kips. Shear is going to jump up by 60 kips. It's going to come straight across. At the first load, jump down by 20, come straight across again, and jump down by 40 at the end. Values are 60 and 40, and positive everywhere. So we note that the peak shear in the beam equals 60 kips. For the bending moment diagram, label it moment in kip feet. Moment is going to jump down by the value of m sub a at the end, so negative 500 at the end. It's going to increase linearly, and the area of the shear, 60 times 5 is 300, so it jumps from negative 500 up to 200, and then it's going to increase linearly again, and the area of this shear, 40 times 5 is 200, so it comes back to 0 at the end. We note that our peak moment is the moment at the end, which is 500 kip feet. Since I'm finding absolute max, I don't need to worry about the sign. Now we're ready to compute the stresses. Sigma max, we'll use the formula sigma equals mc over I, where I for a circle is pi over 4r to the fourth if we're given units in dimensions of radius, and c is equal to r. So we'll go ahead and put everything together. The moment, 500 times a factor of 12 to convert it to kip inches. Then the c value equal to 4 inches. Divide by pi over 4 times 4 inches to the fourth. This computes to 119.4. My units are kip inches squared divided by inches to the fourth, which leads to overall kips per square inch, or KSI. This is sigma max. For the shear stress, we can use the quick result. Tau max equals 4/3 V over A. This occurs at the neutral axis or centroid of the section, and it's actually the only place we know how to compute shear stresses on a circle, but it is the max, so that's what we're interested in. We can easily evaluate this. 4/3 times the maximum shear force of 60 kips divided by the area, pi times 4 inches squared, which computes to 1.59 KSI. That would be our tau max. Okay. By inspection, the numbers seem reasonable for stresses. Sigma max, maybe a little large. Tau max, note that the shear stress is much smaller than the maximum bending stress. And this is typical in any beams with typical dimensions where the length of the beam is much larger than the cross-sectional properties. Generally, bending stresses will be larger than shear stresses, so that's a good check for you. And that completes this example.